Alright, let's go over some introduction to bonding stuff. So, part 1, distinguishing ionic and covalent compounds. Question 1 says, how can you distinguish between ionic and covalent compounds? So you have to remember here that ionic refers to a metal plus nonmetal, and covalent refers to a nonmetal and a nonmetal. Alright, so let's give examples. So an ionic compound, the most common one you'll probably see is sodium chloride, NaCl. This is going to be ionic because we have here a metal sodium and a nonmetal chlorine. Alright, so covalent compound, so carbon tetrachloride, CCl4. We have here the carbon, nonmetal, and 4 other chlorines, which is another nonmetal, which is covalent. So in order to distinguish between ionic and covalent compounds, you have to look at the compound and see if there's a metal in it. If there's a metal, go ionic. No metals, covalent. Alright, number 2. Identify the components of each of the following compounds, metal or nonmetal, and decide if each is ionic or covalent. Alright, let's take a look. So when it says element 1 and element 2, it's referring to these. So element 1 refers to this, and element 2, that's a horrible circle, element 2 refers to this. So if you take a look here, element 1 for this first example is a metal. Element 2, bromine, is a nonmetal. So, based on what we learned up top here on question 1, is this compound ionic or covalent? Well, it has metal, it has a nonmetal. It's ionic. Alright, second question. H2S. So we have a hydrogen here and a bromine or sulfur here. The first element, hydrogen, is a nonmetal. The second, sulfur, is also a nonmetal. Therefore, this one is covalent. Third example, N2O4. First element in N, second in O. And nitrogen is a nonmetal. And oxygen is also a non-metal. Therefore, covalent. Alright, last question. FeO. We have an Fe for the first element and an O for the second element. So the first one, Fe, iron, element 26, is a metal. Oxygen, the second element here, is a nonmetal. Therefore, it's ionic. Alright, moving on to part 2. Electron configuration review. What do we call electrons in the outermost shell or the highest energy level of an atom? They're called valence electrons. Valence electrons. Question 4. Write the electron configuration and identify how many valences are in the following elements. Let's take a look. The first element is nitrogen. So if we look at our periodic table, you can see that nitrogen is element 7. And so we start with electron configuration. Let's try, without using noble gas, let's try it for the regular method for nitrogen, since it's element number 7, it's not anything down way below. So, starting on hydrogen, 1s1, 1s2, right? There's hydrogen and there's helium. So we're going to write 1s2. And then we move down to the second, and we have lithium, beryllium, which is also the S group. So we have 2s2 since we jumped down a row. And then we have boron, carbon, and nitrogen. And so we have 3 of the 6 p groups present. Therefore, we're going to have 2, if I can find where I had my thing, 2 p3. All right, and there's two ways to determine the number of valence electrons. You can count the groups. So if nitrogen's here, it's in group 1, 2, 3, 4, and 5, so it has 5 valences. Or you could also look at the highest energy level, or the energy level. So we have 1, we have 2, and we have 2. 1 versus 2, 2 is higher. So we're going to only look at the ones with the 2s. And then if we look here, we have 2 electrons and 3 electrons. Add those up and you get 5, which is the same as that. All right, let's try the second example. Magnesium, element number 12. Same deal. We're going to try without noble gas notation. And we'll do it on bromine, so don't worry. Magnesium, we're going to count all the way to 12. 1s2, 2s2, and this time we have a full P on the second P sublevel. So we have a 2p6. Then we're going to go down to the third row, and we have a full S sublevel. So 3s2, and that is your answer. Same deal here. Let's look at this valence electrons. Magnesium will have 2 valences because if you look on your group, it's in group 2, which means it has 2 valences. So if you're asked, if you have, say, selenium, which is element 34 right here on group 6, then it will have 6 valence electrons. Lastly, bromine. Bromine's element 35 here in group 7. It's a halogen. We're going to try the noble gas notation. So go ahead and find bromine, 35, element 35, and go backwards, which is leftwards, until you get to the next noble gas. So going back from bromine, 35, selenium, 34, 33, 32, 31, all the way to potassium, 19. And that's not a noble gas. You have to go one up. And so the closest noble gas that bromine's already covered within the electron configuration would be argon, element 18. So get our bracket, put argon in it, that's Ar, element number 18, and then start from there. So we had argon, and now we're going to start at potassium, element 19, and go all the way up to 35, bromine. So that's the 4th S sublevel. So we're going to have 4s2, and remember that the 3D group comes in after. We have a full D because it's not a transition metal, and the 1, 2, 3, 4, 5, 4p5 in order to reach bromine. And so if you look at it, our valence electron is going to be 7 because it's a halogen. You could also look at, since there's 4, 4, and 3, look at only the 4 since it's the highest. And then go ahead and look at the electron exponents, which is 2 plus 5, which is 7. All right. Let's take a look at 5. Fill out the table below using electronegativity values and what you know about ionic and covalent compounds. Alrighty, so you will have to do some online researching here. Alright, so it's asking for cesium fluoride. Cesium's element 55. Fluorine is element 9. So, cesium, which is a metal in the alkali metal group in the periodic table, so it will be ionic. The electronegativity values, we're going to find cesium. Let's see if I can Google this real quick. Cesium electronegativity is 0.79. And you don't memorize these numbers. These are, who memorizes these? No one. You'll just Google them, or it'll be given to you on an examination. Fluorine electronegativity is 3.98. 3.98. And so if you look at this value alone for cesium fluoride and you calculate the difference, you just subtract it. So you always subtract the largest with the smallest because you don't want a negative difference. 3.98 minus 0.79, which is, give me a second, 3.98 minus 0.79 is 3.19. And which element's the strongest? Well, compare the electronegativity values. Cesium has 0.79, fluorine has 3.98. Which one's bigger? Fluorine. And that's your answer. All right, and are electrons transferred or shared? So a key thing to remember here, that if electrons are transferred, they're going to be ionic. If electrons are shared, they're going to be covalent. And the easiest way to remember this is kind of think about the word of covalent. So valent, what does that make you think of? Well, valence electrons, valence, right? And so co means together or shared. You're sharing together. So since you're sharing valences together, you're going to have a sharing of electrons versus ionic where it's being transferred. So with that knowledge, cesium fluoride, an ionic compound, will have a transferred electrons. All right, let's do one more. I will not be Googling all of these because I have a life. Um, let's see. Titanium. Titanium has 1.54. 1.54. Oxygen has 3.44. All right. Let's do this first. I skipped over it. Titanium's a metal. Oxygen's a nonmetal ionic compound. The difference, all you got to do is literally subtract 3.44. Let's write this down. 3.44 minus 1.54. And you might be wondering, why aren't you subtracting 3.44 from 1.54? And well, because it'll give you a negative number. You don't want that. And so when you do this, you will get 1.9, which is your electronegativity value. And for the which element strongest question, look at the numbers, compare it, and you will see that oxygen is higher because it's 3.44 versus titanium with 1.54. Therefore, oxygen is the strongest element. And because it's ionic, we always know that transfer of electrons occurs. All right, let's take a look at this. This one for nitrogen. It's the special one. Well, what you might be wondering, where's the other element? Well, nitrogen is N2. And you might be wondering, why in the world is nitrogen N2? Well, it's diatomic. So if you were to take a sample of the air, most of our air is nitrogen. If you were to take a sample of that and look at nitrogen, it would be a double, you would find two instead of one. So if you dig up the ground and you find carbon, you'll only find one carbon. But if you somehow extract nitrogen, you'll find two nitrogens. And so since nitrogen is a nonmetal, here, let me scroll up a little bit so you can see the top part. Nitrogen's a nonmetal. It's going to be covalent. It's bonded to itself. And this bond, by the way, isn't accurate. You'll learn it in a future unit. So the electronegativity value for nitrogen is 3.04. All right. And so the net difference is 0. And so which element's the strongest? Well, neither, but theoretically nitrogen is the strongest. But you could also, here, let me scroll down a little bit, nitrogen and neither or both. All right. And are electrons transferred or shared? Well, a nitrogen isn't going to steal another nitrogen's electron. It's going to share it. But the other way to think about this is since it's covalent, it'll share. So they are shared. All right, number 6. Using what you found in the table above, complete the following rule about the electronegativity difference and bond type. When two elements have an electronegativity difference greater than blank, they will form a blank bond. When two elements have an electronegativity difference less than blank, they will form a blank bond. So I don't actually know the numerical value of this, but to give a rough estimate, around if it's 1.2 or greater, they will form an ionic bond because one element will have more electronegative tendencies than another element, so it'll take that electron to itself instead of sharing it. When two elements have an electronegativity difference less than, I don't know, it's like zero point 0.6, it will form a covalent bond. Don't quote me on this value because I am not for sure. But usually anything under 1, like zero point 0.4 or zero point 0.3, it will be a covalent bond because their difference isn't that big. But if it's greater than 1, say, like 1.5, it will definitely be ionic because the electronegativity difference is so much greater on one element than another. All right, let's see. What pages do I need to go to? Here it is. What is the octet rule? This is question 5. The octet rule, well, what does octet sound like? Oct, 8. Octet rule means that you have a full 8 electron outer shell. So, if you look at your periodic table, what are you talking about, right? The octet rule. Which elements, which group of elements have a full outer electron shell? Well, take a look at the noble gases. Helium, neon, argon, krypton, xenon, and radon. These noble gases all have a full outer shell. So if this is an element and this is their outermost shell, I know this is a horrible drawing, but they have 1, 2, 3, 4, 5, 6, 7, and 8. The fullest it can be in the outer shell. All right, so let's take a look at question 6. How and why do elements form ions? So elements can form ions because ions are a charged variant. Basically, it's like say we have a sodium, right? We can have like a sodium plus 1 plus, sodium 3 plus, sodium, I don't think this even is possible, but sodium 12 plus, right? Just giving dramatic examples to show ions. So you can have the same base element but it has different amounts of electrons. And so, why do ions form? Because you either gain or lose electrons. You gain or lose electrons. All right. And so, if it gains electrons, right? You have to kind of understand what electrons are. Electrons are negative. Negative. So, if you gain an electron, you gain negativity, which means that you become more negative. Just because you're gaining electrons doesn't mean you're gaining positivity. You gain electrons, you become more negative. Vice versa, if you lose electrons, you're going to lose the negativity and be more positive. And so, in order to answer the question, I guess, how and why do elements form ions? Because they gain or lose electrons, and this is a natural process. 7. Identify the charge that the following elements would have when they form an ion and write the electron configuration. What noble gas has this electron configuration? Taking a look at nitrogen. Nitrogen, element 7 in the periodic table, has a charge of 3 minus. 3 minus. And the way I know this is because the hydrogen, the alkali metal group, has a +1. Beryllium group, the alkaline earth metals, have a +2. Boron group has a 3 plus. Carbon group has a ±4. Nitrogen has a 3 minus. Oxygen, element 8, 2 minus. Fluorine, which is a halogen, which has a value of 1 minus, and helium has 0, because, or the whole group for helium has 0 because they're noble gases with a full octet. So knowing that element N, nitrogen, has a charge of 3 minus, let's write the electron configuration of the ion. When I write these, I always start with the regular element. Forget the ions for now. We're just going to write the electron configuration for nitrogen first. 1s2, 2s2, 2p3 is our value for nitrogen. And when we have a charge of 3 minus, we gained 3 electrons because the more negative you are, the more electrons you gained. Question 6, that's what we talked about. If you gain electrons, you become negative, and we are negative, so we gained electrons. So instead of having a 2p3, we're going to change that to 2p6. We added 3, and we had a full p shell now. So 2p6. And that is the electron configuration for element nitrogen. And if we look at our periodic table, 7 element nitrogen, you give 3 electrons, so you become more negative. Move it to the right, right? Because you're getting more electrons. You need more protons to balance this out. Move it 1 to the right, oxygen. Another to the right, that's the second one, fluorine. And move it the third, final time to the right. You get element 10, neon. So the noble gas with the same electron configuration. Let's write this. Electron configuration. And if you're confused by what EC means, it's electron configuration, it's this. Don't confuse yourself. Noble gas is neon. All right, let's skip magnesium. You guys can do that as practice or something. And let's take a look at bromine. Bromine has its element 35. It's a halogen, right? Let's write the electron configuration. So bromine has a charge of 1 minus because it's a halogen. It's in group 7, fluorine, chlorine, bromine. And if I use the noble gas because I ain't writing all that out, we have argon. And let's take a look here. 4s2, 3d10, and 4p1, 2, 3, 4, 5. And instead, we we gained an electron and we became more negative is what I'm looking for. So instead of 4p5 we had earlier, it's going to be 4p6. Same deal with here. We gained an electron and it became more negative. And so the noble gas we go bromine and we go right one and it's going to be krypton, Kr. It's a horrible K. All right. Part 3, Electronegativity Review. How do we define electronegativity? Think of this as electronegativity. What's negative? Electrons, right? Electronegativity, electrons. So it's let's see, the force in which an element attracts electrons. All right. On the following periodic table, use arrows to indicate the trend we see for electronegativity. You're going to have to memorize this. We're going to go all the way to the right like this. We increase in this direction. So we increase up electronegativity. I'll write that somewhere else. Electronegativity. Electronegativity increases up and right. All right. And it ends right here at fluorine. So the general increase in trend would look like this. I'll draw that a little sideways this way. All right. And it'll stop at fluorine. That is how I write it. All right. Here. 7. Explain the image below using the terms electronegativity, electron transfer, electron sharing, ionic bond, and covalent bond. All right, that's a lot of words. Jeez. Let's see here. So we have here on drawing 1 a transfer of electrons. Atom 1 and atom 2, a metal and a nonmetal. We know that's ionic. And this electron is being donated to this. So an example of this, A and B, a great example actually, is sodium chloride. Sodium is plus, 1 plus. Chlorine is 1 minus. Right? 1 minus, 1 plus. So, because it's ionic, they're going to transfer their electrons, not share them, right? Transfer. So this valence, 1 valence the sodium has, will donate away to the 7 in chlorine. And that's all it's saying. So the electron transfer, right? The electron from sodium is transferred to chlorine. And now it's an ionic molecule, right? I just wrote it there, but we know now it's an ionic molecule, right? And so compare that now with this diagram here. This one has 7, this one has 7. We're going to share this electron so both are happy. Say element B here gave away its electron. Now atom 1, element A, has 8 electrons, but atom 2 just lost another one, so now it has 6. No one's happy that way except for atom 1. Therefore, if you share an electron and they both have 7, they both have 8 now, and so they're both happy. That is how the sharing works. Let's see if I can come up with a good example for this. CCl4 is too common. Let's just do CCl4, right? My favorite. CCl4, right? Chlorine, carbon, we have a 4 plus. Chlorine has a 1 minus, and so you need 4 chlorines for 1 carbon. So when this happens, the carbon's in the middle, and the chlorine shares this electron within, the carbon. And so that's a little complicated, but all I'm getting at is this process here is happening. The sharing of electrons is occurring in covalent bonds. All right, question 8. Let's see. What holds 2 atoms together in an ionic bond? So let's see. Probably what it's asking about is the transfer of electrons is holding it together. So if element A transfers an electron to element B, then that bond, the ionic bond that occurred within the atoms, is going to hold the atoms together. So like sodium chloride, NaCl, this transfer of electrons holds together this ionic compound. So what holds 2 atoms together? The ionic transfer of electrons. Similarly, what holds 2 atoms in a covalent bond? Well, covalent bonds share electrons, so it's going to be the covalent sharing of electrons will hold these covalent compounds together. Alrighty, moving on. Part 4, electron dot diagrams. Read this. Electron dot diagrams, aka Lewis dot structures, are a very easy way to represent valences in an element and to model bonding. To draw these, you place the element in the middle, draw a dot for each valence electron. And so when you think about it, the dot should be written in pairs because um, it's one of the rules you'll learn. Oh, it actually says that right there, Hund's rule. So you'll realize that each. Here, let's take a look at the 3D sublevel. So you need to have one electron in each slot available before giving another one pairs. So each slot needs to hold one before giving it two, is what it's saying. It's a little complicated. It's a review from last unit, but if you understand that, you're pretty much all set for Lewis dot. It's like the easiest thing you do in this unit. So looking at oxygen, let's see, element of a single element. So let's try, since it gave oxygen, let's try nitrogen. All right, element 7, nitrogen, right? So nitrogen, you put N for nitrogen, it's the symbol, and you give it how many electrons? Well, figure out how many valences nitrogen has. It has 5 because hydrogen is group 1, beryllium group 2, boron group 3, carbon group 4, nitrogen group 5, and group 5 have 5 valences. You draw a dot. It doesn't matter where you can start here, you can start here, you can start like here. It doesn't really matter. But I start from the top because that's like the most logical thing to do. Nitrogen, 5. You're drawing 5 dots. 1 dot here, and then you can't draw it here. You have to draw it here. Why? Because you need to give one side. So we have 4 sides: side 1, side 2, side 3, and side 4. So you need to give one dot to each side before giving it another dot. That's all it's saying. So give 1 here, 2 here, 3 here, 4 here, and the 5th one you can give a second one to the first one where you started. So that is nitrogen. Let's take a look at some more complicated ones where it has the bonding model. Where does it have that? What is wrong with this worksheet? All right. All right. Let's take a look at this then. And we're gonna circle back to this page here because I think I skipped it on accident. Sorry about that. So sodium. This is ionic. Remember, sodium chloride, metal, non-metal. So it is ionic. We're gonna have the sodium, which is 1 plus, Cl 7 minus, or sorry, 7 valences and 1 valence for sodium. That valence is going to move here, and now we're gonna have sodium here and chlorine here, and they're gonna be very happy, ionically bonded together, because sodium gave chlorine its electron. Draw the electron dot diagrams for the following elements and ions. Let's try with K. Potassium, element 19. K. It has 1 valence. It's a group 1 element. 1 dot. Mg, magnesium. Same deal here. This is an alkaline earth metal. Mg, write it, and then it has 2 valences because it's group 2, and that's it. Al, aluminum. It's going to be group 3. It has 3 valences. 1, 2, 3. You're done. Sulfur. You have 1, 2, 3, 4, 5, 6 for sulfur. Put the S, 1 dot in each side, remember, first, that's 4, and then the 5th one goes here, right next to where we started, and then you just keep going that way. So once you start going this way, you're going to keep going around and giving it this way. Alright, nitrogen, we already did that one, but let's do it again. Nitrogen, N, put the symbol first, and it's a group 5 element. 5 valences. 2, 3, that's a terrible spot to put that. 3, 4, and 5. Iodine, last one, group 7 halogen, element 53. Put the I, 1, 2, 3, 4, 5, 6, 7. You're done. Draw electron dot diagrams to represent the ionic bonds formed between the following pairs of elements. Potassium and iodide. Let's try this one. Potassium has a 1 plus. We all know that. And it has this dot 1 electron representing. We have iodine here. It has 7. 4, 5, 6, 7. And it's 1 minus. This is going to be donated because potassium is a metal. It's going to be transferred, not shared. Oh, what is happening? And similar to what we saw up here, we're going to write this. So when the potassium gives its valence to the iodine, it's going to make K plus, and the full, we're going to draw 8 on iodine because potassium gave it away. So we have no dots on potassium. And we're going to put the minus. You do need to put the charges, not necessarily on these, but you do need to put it on here or they will count you off on the test. Make sure you know that. All right, let's try here. Mg and S, magnesium and sulfur. Magnesium is a metal. Mg, it has a 2 plus charge. 1 electron, 2 electron. Sulfur. Sulfur is element 16. It's going to be in the group of oxygen. 6 valences. So it has a 2 minus charge, by the way. 2, 3, 4, 5, and 6. So we're going to detail this electron coming here and this electron coming here. Draw little pointy arrows if you want. I'm going to draw this. Mg, 2 plus. We draw full sulfur. Full sulfur, and a 2 minus there. Last one. Potassium and nitrogen. We already drew potassium. It's K plus. And it has 1 valence. It's an alkali metal. And nitrogen. Nitrogen is going to be element in the nitrogen group, which is group 5. 5 valences. Right? Something's wrong here, right? Clearly you can see that you need 8 for an octet, which means they're happy. That's where we're going to go. But nitrogen only has 5, and which means it needs 3, but we only have 1 K. What the heck, right? Well, if you look at the periodic table, we know that K is 1 plus. Nitrogen's 3 minus. You just need 3 Ks. So if you look at this, you're going to see that we're going to have another K and another K. We're just going to have 3. And this one's going to go here. This one's going to go here where it's missing. And this last electron goes here. And so if you write this, let's see how we want to write this. Let's just do it this way. K, you could write it in a couple different ways, I'm assuming, but don't count me on this. We're going to do a 3K plus here. And then we're going to do a nitrogen with a full octet, 8 on the Lewis dot structure. We're going to do a 3 minus. You can either do it like this, or let's see, K plus, K plus, K plus, nitrogen, 1, 2, it's a horrible dot, 1, 2, 3, 4, 5, 6, 7, octet with 8, 3 minus, and that would be your answer. Alright, going back to this page, I don't know why I skipped that, or how I skipped it, but apparently I did. For each of the following pairs of atoms, circle the element that is the most electronegative, or most electronegative, or negative. What is wrong with my pronunciation today? All right, so find magnesium on the periodic table. It's going to be element 12. Oxygen is element 8. And so based on our trend that if we have, let's see if I can draw a periodic table here. Kind of like this. Right? Our trend is going to increase up and right and stop at fluorine, right? For I'm not going to draw that. Electronegativity, right? We know that. So if magnesium's here and oxygen is all the way up here, obviously oxygen will have a greater electronegative value than magnesium. All it's asking is circle. B. Nitrogen and carbon. Nitrogen is element 7, carbon 6. It's nitrogen one more right than carbon, right? It's element 7 versus 6. So nitrogen is going to have a greater okay, where's my cursor? Nitrogen will have a greater electronegative value compared to carbon. C. Bromine and fluorine. All right. Bromine is element 35. Fluorine is element 9. If you look, it's on the same group, but fluorine is two rows more up than bromine. Therefore, fluorine will have the greatest. If you always see fluorine, it's going to always be the most for electronegativity. So last one, sodium and francium. Na is 11. Fr, francium is 87. So same deal here. It's more up. Sodium is 1, 2, 3, 4 rows more up than francium. So it will have the more electronegative value. Chemists have assigned electronegative values for almost all the elements on the table. Go to this periodic table, also link on Canvas, or you can Google it. The electronegativity values will appear on the bottom. List the electronegativity values for each of the following elements. We're not going to do that. We already did it in our example. Let's just do one. Fine. Magnesium and oxygen. Search it up on Google. Magnesium electronegativity 1.31. There it is. Right? It's that easy. Just Google it. 1.31. Oxygen. Right? Oxygen electronegativity. It gives you 3.44. Very easy. Just Google it. Which one's the greater? Oxygen has a greater value than magnesium. So which one's more electronegative? Oxygen. That's it. So by it saying, do these values agree with your answers in number 3, it's basically asking you to prove that you're right and this trend is correct, right? Because oxygen's more up than magnesium, which is like here-ish, right? It's going to have more electronegativity. But if we look at the numbers, it proves that. That's all it's saying. All right, read this. Electronegativity, En, plays a huge role in the type of bond. If the electronegativity values are very different, like, remember, if we take the difference of this, it's like 2 or like 1.8 something. I'm not going to do the math, right? It's greater than 1. It's a huge value. So it's going to be a ionic bond. Well, we know that because it's magnesium and a metal. But it means, what the ionic bond means is that the electron is going to be stolen from the weaker atom. Now, if you have a covalent where it's like a 0.5 or 0.4, 0.3, right, electronegativity values are kind of small. That means the elements are, equal, kind of half and half with the strength. Neither wins, they share it, right? And we see this happen with covalent bonds and covalent compounds. And giving a little refresher, ionic is metal plus metal, or metal plus non-metal, and covalent. This is for compounds, by the way. Covalent compound is going to be a non-metal plus non-metal. All right, and that's all you need to know. Good stuff.